Okay, so on this page, we got 4 ramps. Each of them, we have a block. They're not all the same mass. We're given a couple different angles, so theta and 2 theta, and then different mu k. So yeah, that's not another m, it's that new Greek symbol mu k. It's supposed to be the coefficient of kinetic friction. And so kinetic right off the bat tells us what about the object? It's moving, all right? Now, we don't know if it's moving up or down, but that's okay. It doesn't matter, okay? And so we'll just say it's going down the ramp because in order to go up, it's still going to accelerate down. So we'll just say they're all moving downward, okay? Just for consistency. And so the first ranking is normal force. So it's on a ramp. Let's go ahead and draw one of the force diagrams. Step 1 on a force problem, always a good idea to draw a diagram. And overall, they're all at an angle. They all have a mass and they all have some friction. They may not be equal in magnitude, but the overall look for those diagrams is going to be the same. And so what forces are acting on any of these blocks while sliding down the ramp? Gravity. Does gravity care that it's on a ramp? No, gravity's always pulling straight down. And this is our biggest force, remember? What other force is acting on the object? Due to a surface. There's friction, and so I originally made the decision they're going down the ramp, so kinetic friction will act on them up the ramp, okay, parallel to the surface. And so, again, they're all at a different angle, but overall, this frictional kinetic force is going to be up the ramp at some angle. Surfaces also give us another force. The one we're ranking, normal force. So normal force, by definition, is drawn how? Perpendicular to the surface. So if all of these ramps are tilted, okay, then it's going to be drawn up and to the leftish, whatever direction you have to tilt your head. And so up and leftish. And that's it. Now, on purpose, I drew gravity as the biggest force because who remembers what's true about normal force on a ramp? Does it equal Fg? No, Fn on a ramp equals what? What do we do special and unique to force diagrams for an object on a ramp? Right. And so we have a new perpendicular axis and a new parallel axis. If you want to call them new X, new Y, you can. But with this, normal force and frictional force, well, they line up on the new axis, but gravity does not. And so what's unique about ramps, you draw the components for the gravitational force. And this is where students mess up, okay? When you go to draw the triangle, here's what you should pay attention to. So FG perpendicular opposes your normal force because 99% of the time, Fn equals that perpendicular component of gravitational force. And that is actually on the new y-axis, Fg is on the old y-axis. And so there's your angle that's equivalent to your ramp angle. And again, I know it doesn't look it, but you got to go back to, I don't know, page 16 where we started ramps, okay, and did our little lesson, or maybe it was 15, and do that new to old axis shift. And then we can complete the triangle by doing the parallel component. And so notice the way I have it drawn, the parallel and perpendicular components should be 90 degrees from each other. Check. So that FG is what part of the triangle? the hypotenuse. Okay, and if all that checks out, you probably have it drawn correctly. And so not that you had to do all that, but if you were struggling on how to find the FN for an object on a ramp, this should help you, okay? Force diagram. I will always preach force diagram as step one. Always, 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 okay? Because this, what we're about to do to get the FN, is based on the diagram. And so FN equals FG perpendicular, which has an equation that you can memorize, okay? It works 99% of the time, so I think it's safe enough to memorize. And it's equal to mg, who remembers which function? mg is fg, right? Hopefully I didn't just pull that out of nowhere for you. What trig function do we use for the perpendicular component? Cosine, because the perpendicular component is adjacent and FG, mg, is a hypotenuse. And so whoever, they all have the same gravity here, right? Assuming they're all on the same planet. And so it depends on who has the biggest mass, but also watch out, cosine theta. We've got theta in A, and then B, C, and D all have 2 theta. And so we got to consider as theta increases, what happens to cosine theta? And if you're like, I don't know, I don't have that memorized, let's pick a couple numbers. How about 30 and cosine 60? 30 to 60 is an increase in theta. Grab a calculator, make sure you're in degree mode. And if there's not a calculator on your desk, send somebody. I plugged them all in so they could charge. Cosine 30 is what decimal? 0.86. And then cosine 60 is 0.5. And so as theta increases, cosine theta does what? Decreases. And so who's going to have the biggest normal force? And it doesn't tell you, but my rankings, I usually do greatest to least, okay? And so if we go with that mentality, who has the greatest normal force? Well, it's whoever has the greatest mass and the smallest angle, right? And so who is that? Greater masses, smallest angle, so our greatest normal force is going to be which of our 4 samples has the greatest mass and smallest angle? Who has the greatest mass? I know it's Monday after a time change, but M or 2M, who has the greatest mass? 2M, so it's between A or B. And so who of A and B, who's going to have the greatest normal force? Well, who has the smaller angle? A. And so A is going to be the greatest, right? Who has the least? Let's go that way. Who has the smallest mass and biggest angle? Who has the smallest mass? C and D, bless you. Who has the biggest angle? Bless you. Same, right? So C and D have the same. And so we know that somewhere in our ranking towards the end, maybe C is equal to D. They have the same mass and theta. Well, what about B? Is B automatically next? Or is there something in B that makes it have more normal force than what we just decided in C and D? Yeah, it's got the same angle as C and D, but it has more mass. So that'll give it a greater normal force. Make sense? And so A is greater than B is greater than C equal to D. Now, if you wanted to, if you're like, oh, I can't do this without numbers, you could make up some numbers, 30 and 60, right? 1 mass, 2 mass. Notice we didn't even need the coefficients. What we did give numbers for, right? We didn't even need the coefficients. Normal force does not depend on the frictional force. But acceleration does. Next ranking, acceleration. Now, acceleration does not appear in a force diagram. So refresh my memory on Newton's second law. What does acceleration depend on? Or it's an equation on the formula chart. Net force, it's a ratio of net force to mass. So again, if we start the ranking greatest to least, then the greatest acceleration is going to have the greatest net force and the smallest amount of mass. Y'all remember Newton's second law is more than the equation. It's really about the relationships. And so acceleration is directly related to the net force and inversely or indirectly related to the mass. So whoever's going to have the greatest acceleration is going to have those two relationships. Now the mass, we can tell masses from the picture, but did we give you net force? No, so maybe we go sum the forces from our diagram. Step 2 on every good force problem. After you get your FNet, sorry, I can't talk. After you get your diagram, at some point, be ready to do an FNet statement. Now, we just dealt with the perpendicular. Is everybody good that it's not accelerating in the perpendicular? I should have said that earlier. That's why those two FN and FG perpendicular are equal. It's because FNet in the perpendicular direction is equal to 0. And on ramps, y'all, we don't levitate on ramps. We don't sink into the ramps. Okay, I've never seen a problem with either of those. And so that's why most times, 99% of the time, those two forces are balanced. But it's going to accelerate in the parallel. So let's go back up here. Let's sum the forces in the parallel direction. I said we're moving downward. I didn't say if it was positive or negative, but I'm of the mindset forward is positive. So what if down the ramp is our positive direction? What force has a positive down force down the ramp? Who's bringing it down the ramp? FG parallel. I'm so glad you included the parallel. Okay, it's not FG, that's a hypotenuse. That's not in the parallel direction. And then there's more to it. There's another parallel force. What force is parallel to the surface always? Kinetic friction. And so it's going up the ramp, so I'm going to make it minus. So there's our summation, our net force statement for the forces in the parallel axis. Does not have acceleration yet, but don't forget F net equals what? MA. It's Monday morning. Let's get our brains going. This has to be quick on y'all's part, okay? This has to be gut instinct, muscle memory, right? F net equals what? And everybody says? MA. F net equals what? MA. I'm going to keep going until I hear a resounding answer. F net equals? MA. Okay, I'll take it. It's corny, but hopefully you don't forget, you know, on next week's exam, on the May exam, F net is not a force that you can actually make contact with somebody. I can't F net you. F net is the summation of it all, and it leads to mass times acceleration. Now, what can we plug in for FG parallel? Go back to your triangle. What part of the triangle is FG parallel? Sine. We're going to use the sine function because it's opposite that angle, that theta. And so similar to before with normal force and perpendicular, but we're going to say mg sine theta. And that was one of those memorize it if you want type of equations. And then frictional force, we got our new equation. What's our new equation for kinetic friction? It's kind of on the formula chart. They don't specify kinetic. Force of friction equals the coefficient of kinetic friction times normal force. Well, what have we already said about normal force? It's equal to mg cosine theta. Yeah. And you're like, why do you need to put that back in? We already dealt with that. Well, there's sometimes little simplifications. I don't want to call them tricks. But notice, does the acceleration depend on the mass? When you put every variable in its simplest terms, notice m, m, m. I got three terms, three forces there. M on the left, m in both terms on the right. And so everybody brought mass to the party. So divide the whole thing by mass and it cancels out. So that's one less thing we have to worry about in our ranking. Acceleration does not depend on your mass here. Now, warning, if they had a string and there was a tension force, can we actually simplify tension into simpler terms, into mass terms? Does it get an equation, mg something? No. Tension is like an applied force. And so mass won't cancel if you had something like that. And so acceleration depends on who's going to have the greatest acceleration. And so we already saw with normal force, as theta goes up, cosine theta goes down, right? And so if we go greatest acceleration, we want for cosine theta to go down. What about sine theta? As theta goes up, what happens to sine theta? And you can literally plug in your 30 and 60 to test it for yourself. So sine 30 and sine 60. Cosine 30 is 0.5. What's sine 60? 0.86. And you're like, I've seen those numbers before, right? So with 30 and 60, and then you reverse the trig function, they're kind of complementary to each other, right? Okay. And so as you increase the angle, sine theta goes up and cosine theta goes down. So that's actually good because the one with the greatest acceleration should have the biggest angle. You've played around with ramps before. The bigger the angle, the faster it makes it down the ramp, right? Because it has a greater acceleration. But what about mu? Do we want the greatest coefficient of friction or the smallest? What about friction, that coefficient? Who's going to accelerate more with more friction or less friction? You know this. Less, okay? And so, based on that, not based on mass, it's based on the angle and your coefficient. So we want the greatest angle and the smallest coefficient. And so who's got the greatest angle, smallest coefficient? D will have the greatest acceleration. And then who? The greatest angle next would be C and B. And so between, that's the next greatest angle, right? And notice they have the same coefficient. So if they have same angle, same coefficient, different mass, well, mass canceled out. It was independent. And so B and C would be equal. And then, okay, A must be the least, but let's double check it, right? And so A has a small angle, small acceleration, and comparatively, it's got a big coefficient. And so, yeah, it should have the smallest acceleration. Good on that? So your takeaways, it's a good review question for not only friction, but ramps, which we started last time. Your diagram changes, your FNet, your axes changes. Make sure you write out FNet statements, know what you're looking at. Good deal? Okay. The question below, we're not quite ready for it yet, okay? Not quite ready. And so let's go back to page 15. I think I told you we'd come back to this one. So not to pulleys or system. This is a system, more than one object. We've been doing that, but it's not a pulley question yet. So let's do this one. No ramps, yay, right? Oh, but there's friction. Okay, so this is a friction system type of problem. Now there's not a story with it. And so if you want to make this a stack of books, you can. If you have ever put anything on the hood of your car before you drive off and, oh no, my drink spilled, right? Okay, so that's kind of similar to this. And we've got a 10 kilogram, 20 kilogram, but notice we're only going to apply the force to who? To the 20 kilogram, the bottom block. And you're given some information. The coefficient of static friction, at least with the floor, so both of these are with the floor, and I'll call this M2. I'm going to say variables to start. So M1 at the top, smaller mass M1, bigger mass M2. And they give us the coefficient of kinetic friction. And notice kinetic is less than static. That should be the way it is. What is the minimum coefficient of static friction, aka gripping friction, for the 10 kilogram block not to slip off the 20 kilogram block? They didn't mention the floor at all, so the answer is not 0.3. It may be, but we're going to solve for it. And so we're looking for this coefficient between the blocks. Now we don't know what they're made of, and that's okay. We're not going to just look it up. We're going to use our forces. Step one is what? Oh gosh, muscle memory. Y'all gotta be quicker. I know it's Monday after a time change. Step one on a force problem. What do? Force diagram, right? I've got two objects, so how many diagrams maybe should we do? Two. Now pay attention, okay? We've got for the 10 kilogram block, I'm gonna kind of put that diagonal. I need room for my arrows. And then we'll slide over and do the 20 kilogram block. So let's start with the 10. What forces are acting on the 10? Gravity, and 10 is less than 20. So maybe I give a small FG10 if you want, or FG1, I called it M1. Either way, FG1 is down on 10 kilogram block. What else? There's a normal, but I'm going to get detailed here because it's not with the floor. We tend to just put normal forces for floors or tables, not other blocks, but it's still a surface, right? How big should I draw that normal force? When you push on the bottom block, is anybody going to have vertical motion? No. So what should be true about our vertical forces? Should be balanced, right? And so equal and opposite. Now watching. Fn on 1 by 2. It's not from the floor. You got to be specific here. And if you want to put the tick marks, you can. Any other forces acting on the top block? There's actually one more. The goal of this is when I pull or push on the bottom block, if you have static friction, which they're wanting us to solve for, right? The coefficient, which means it has to be there. What direction is the bottom block going to go? To the right. So we know bottom block is going to move to the right. Let's call that positive. What about the top block? What is the direction of motion for the top block if it grips with the bottom block? Also to the right. Bottom block is going to move to the right too. And if you're like, but it's not, you're not pulling on it. That's right. Who is? It's because of what force that the top block moves forward. Wait, what?
No.
Okay. I didn't know if I misheard or what, but static friction. And look at it as gripping. Yes, the top block is stationary relative to the bottom block. The bottom block is only moving relative to the floor. So remember day one, I was like, point of contact, point of contact, point of contact, right? Here's where that's applied. And so you do have this forward static friction, and watch, just to be detailed, it's on 1 by 2. Don't start thinking it's static with the floor. And if you even want to note to self, it's not necessarily a label, but if you're like, but it's moving, yeah, but not at the bottom between the two blocks. It's stationary, it's gripping. So this is similar to walking, right? We said to walk, something has to propel you forward. My upper body's moving, but if my foot grips the floor, it's stationary at that point of contact, right? Okay. Any other forces on block 1? Top block. We're not touching it, so no applied. We've got a surface, so there's a potential for 2, normal and friction, and then we've got gravity. That's it. What about block 2? The 20 kilogram, the bottom block, what forces are acting on it? Gravity. Everybody better get the gravity, right? All our objects have mass. And it's twice as massive, and so it'll have twice the weight. So I'm going to try, don't get out a ruler, but I'm going to try and, relative magnitude, FG2 would be twice as big as FG1. What else is acting on block 2? A normal force due to the floor, right? And so it's the one in contact with the floor. And so it's going to be exerted what direction? Up. How big do I draw it? It's actually not going to be equal to gravity. And this is part of the challenge. I'm going to draw it bigger than the gravitational force. Don't worry, we'll get there. So Fn on block 2 by the floor. And it's actually alluding to a third diagram. Is the floor only supporting block 2? Isn't it indirectly supporting block 1 as well? And so if we think about block 1 is pushing what direction on block 2? What would we say that direction is? Block 1, which is above block 2, it's pushing what direction on block 2. Their contact force between each other. Block 2 pushes up on block 1. Newton's third law says if 2 pushes on 1 up, 1 pushes on 2 down. And so we're going to add, and maybe I move that FG2 over a little bit, because if you have 2 down arrows, they're different. Don't just do 1 arrow. We're going to tip to tail and say Fn on 2 by 1. And I'm going to highlight that one yellow because those 2 yellow forces are equal and opposite on 2 different objects. They are what? They are supporting which of Newton's laws? Third law. And so note to self, those are a Newton third law pair. So maybe you're remembering the meme, right? I push on you, you push on me. Block 2 pushes up on 1, block 1 pushes down on 2. And so you can put a tick mark here. Not that it's necessarily directly equal to the weight of 1, but it is equal to the weight of 1 because of that contact force between them. This is a system when you have more than one object. They push on each other, right? So that's why the normal force on the floor is bigger. It should equal not only the weight of 2, but indirectly the weight of 1. And I said a third diagram. What would our third diagram be? What if I viewed it as a 30 kilogram system? What forces are acting on that system? Well, the whole thing, Fn on the system by the floor would be equal and opposite to the weight of your system. Good deal on that one? Okay. So let's go back to green. Let's finish up the forces just on that 20 kilogram block. What do we got? I can think of at least 2 more, right? Go back to the picture. Who's 100 newtons? Aren't we pulling or pushing on block 2? And it doesn't matter if it's a push or pull, it's to the right. By the way, oh, we already did say to the right was positive. And so maybe, I don't have any other real numbers to compare it to, but maybe this is FA. All right, what's the other force? Friction with who? Due to who? Say again. So there is a frictional force, a gripping force with the upper block, but there's also friction with the ground. And so let's start with that one. That's probably the more obvious one. What direction, if we move our system to the right, what direction and what kind of friction do we have with the floor? Kinetic friction to the left. And so we've got this FFK on 2 by the floor. But there's another friction, and this one is the one that you don't really see until you take a system type approach. If block 2 is responsible for pulling, gripping and pulling block 1 forward, that's between 2 objects, right? On 1 by 2. Well, isn't that grip happening in the other direction as well on block 2? And so it was a rightward gripping friction on block 1. And so we're going to have, and let me just move some stuff around so it doesn't clutter too bad. I'll say this is the 20 kilogram object. We're going to have another frictional force on 2 by 1. And this is, I'm going to label it, this is the grip at the top of the object. Does that sound familiar? I grip on you, you grip on me. New highlighter. What have we identified? Equal and opposite forces? We've identified another set of action-reaction pair, Newton's third law pair, right? And so these are a Newton's third law pair. Okay, I grip on you, you grip on me. 2 grips 1, 1 grips 2. So these are between the 2 objects, right? Okay. Well, that's it for block 2. And to take it into account, you got gravity, check. And then it's anything touching. So it's touching the floor. We have a normal force and a frictional force due to the floor, but it's also touching block 1. And so remember, any surface can have an option, a potential of 2 forces each. And so it's touching block 1. It has a normal force with block 1 and a frictional force with block 1. So that's it. And the applied force, right? Okay. So here's the beauty. I think we've seen this once or twice before. Here's the beauty of those action-reaction pair, Newton's third law pairs. When you take a system approach, when you view it as a 30 kilogram collection, those pairs cancel out. They're internal to the system, okay? And so I don't have to worry about them on the bigger diagram. So on the bigger diagram, we've already got it started. We've got the weight of the 30 kilogram system. We've got the normal force on the 30 by the floor. And aren't we still pulling on the system? And that's the same FA as it was before. And then there's one more force on the system. Who is it? Who wouldn't cancel? Kinetic friction with the floor. And so I'm going to draw that in. And again, these are, I tried to be a little cognizant of magnitudes, but we don't really know numbers yet. But it's on the system by the floor. And so notice, at least this one, this example, I've done the most descriptive labeling on my force diagram. Okay. And so note to self, on system diagrams, Newton third law pairs, you can also call them action-reaction pairs, cancel out. And the reason, because they are internal to the system. I push on you, you push on me doesn't work when we are considered one object, right? Okay, give that just a second to settle. Ask me questions about the diagrams. We spent a lot of time with it, but it should make the rest go quicker, okay? And I highly recommend drawing the individual diagrams as well as the system diagram, because depending on what you're solving for, it could be helpful to do either or. Any questions before we move on? Yes. The friction that I've highlighted in blue. So that frictional force, don't think of it as a kinetic slipping friction. It's the gripping friction between the 2 blocks. And so that's that upper surface. Oops, That's that upper surface where they interact. And so if I pull on block 2, block 1, if I pull too much, what might happen to block 1, by the way? Should I demo? Would seeing a visual help? Let me get a couple books. Okay, now these are going to be same mass, but overall the spirit is still the same. Let me start here. 2 books, object 1 on top, object 2 on bottom, right? If I just push the bottom block decently, right, Goldilocks, notice, and they can tell you I'm not touching the top block. Look, the top block comes with. That's the example we're doing, right? But what if I push too quick or pull too, here, I'm going to pull bottom block. What if I pull too much too soon? Is grip going to be enough? So just that initial part, what did you see the 2 do? It moves, they slip past one another, right? Right? It didn't grip and come with. You see the difference? Maybe that's a tomorrow problem. Today, I pulled on the bottom just enough so that I don't overcome the static max of the top block with the bottom block. Does that make sense? Okay. And so that's what we're looking at here. We're not overcoming that static max, which is actually the concept we got to consider to solve for this. And so what are we solving for? I've already forgot. What is the minimum coefficient? So we're just looking at that minimum amount that we can pull on block 2 and have enough maximum static friction, that's weird, right? In order to grip and move, okay? And so we're solving for that force that cancels out. Do I want to use the system approach to solve for something that cancels out? No. And so let's use, I don't know, what do you want to write a FNet statement for? Block 1 or block 2? I just assumed everyone would be like, block 1, there's less forces, it's easier, right? Okay, so let's try that. Block 1, I had pink. And so F net in the X direction, because friction on block 1 is in the X direction, equal, and it's block 1. So anytime you have more than one object, please use subscripts. Be nice to yourself. So there's only one horizontal force, right? And it's that frictional force, it's forward. And so it's a positive frictional force, static, on 1 by 2. And I'm using full description because that's what I want you to look at in the diagram. And it's this force that we're going to use to find the coefficient of friction. And so F net equals what? And everybody loudly says 3 people. Okay. MA. So let's get specific. Which mass? Is this a 1, 2, or 3? 1. I'm writing it based on the diagram of block 1. And so subscripts, be nice. And which acceleration? Well, we specified it's a horizontal. And then what can we plug in for the force of static friction? Well, whenever we go to solve for it, I know it says minimum here, but they're just saying like, what's the slickest type of surfaces we can have to maintain that max grip. And so just a reminder, with friction, you've got this graph to look at. Static is on the left-hand side, and that maximum grip is that greatest number. And depending on what surface, it'll have different values. And so I know that it says minimum and I'm saying maximum. They are referring to kind of 2 different things. okay, in the spirit of friction, but we want to know what's the slickest surfaces that we can have to have maximum grip. Does that help? Okay. And so we'll plug in our new coefficient of friction equation, newish, right? Couple days now. And it's that mu s Fn. Now we had several Fn, so let's get specific. Which Fn am I going to use here? Well, it's from the first diagram. So it's Fn on 1 by 2. Well, we said earlier, this helped balance Fg1. And so we can plug in Fg1 for that normal force, bring everything else down. And so these two are equal because of Newton's first law, they balanced on block 1. But wait, there's more. How do you find the gravitational force of an object? mg, which mass? 1, right. Subscripts, let them help you. And if you take it to the simplest terms, what do you notice happens to m1? It cancels out here, okay? And so it cancels out in this statement. And so we're trying to solve for that mu s. So divide both sides by g. And notice I just need the acceleration and divide by g. And there's our answer, right? Oh, did they give me the acceleration? They did not. And so this isn't a one-step problem. We got to pause here and we got to go find the acceleration. And we've already used Fnet in the horizontal for block 1. We know there's 2 things unknown. By the way, in math and physics, we do it commonly. If you have 2 unknowns, you need at least 2 equations, right? And then we substitute solve. And so we got to pause here. Well, let's think about the acceleration of that top block is dependent on the acceleration of the second block. Would you agree with that? And I'm only pulling on one, but assuming they have enough grip between the blocks, aren't both blocks going to accelerate at the same rate? It's all happening because of that applied force, right? And the grip force. And so I'm going to switch over to a system approach and solve for AX. And my reasoning is A1X is equal to A2X. They're moving together. They're both starting from rest. There's enough gripping friction between them, right? And if they're moving together, you could say that they have the same system acceleration. And so that's why doing your system can be helpful. Okay. And so looking at our system diagram, just in the horizontal, let's write an Fnet statement for the system. And so what would our Fnet statement for the system be? Look at your blue diagram. Look at the horizontals. We pull to the right. Friction kinetic pulls back with the floor to the left. Yes? On the system, by the floor. So they gave us the newtons. They gave us how much applied force. We do need to calculate, and it's okay, they gave us enough. But before we calculate that friction, let's break it down. Fnet equals group. Okay, 4 people. MA, so we said we're solving for the system horizontal acceleration, which is going to be the same acceleration on all. What mass are we going to use? in blue here. System equals, well, FA doesn't get its own equation. I can't plug it in. And I'm not doing numbers yet, so variable form stays FA. Minus, what equation can we plug in for that kinetic frictional force? Our newish equation of coefficient times normal force. Now they gave me the coefficient in the picture. What about the normal force? Which normal force is this? It's the system, on the system by the floor. Now I'm going to go to my diagram. What did we say about the normal force on the system on the 30 by the floor? FG of the system, right? The floor is supporting the whole entire system vertically. And so we can plug in, one more plug in, it's the mass of the system times gravity. And these balance because of Newton's first law on the system. And then just bring everybody down. Almost to numbers. All right, before I plug in numbers though, does mass cancel? It doesn't. Why doesn't it cancel? It's not an FA. In order for mass to cancel, if I have 3 force terms, I got to cancel it from 3 force terms, right? Mass, mass, mass. But FA doesn't break down. And so note to self, just because mass cancels in one equation doesn't mean it cancels in all. So just be careful, right? And so let's solve for that acceleration here. We would divide the whole thing by mass system. Oops, I don't know what happened there. And so yes, it could cancel from the right side, but I'm just going to leave it. To me, if it doesn't cancel from all, I'm not going to cancel it. And so acceleration in the horizontal for my system, the applied force they said was, sorry, I got to go back, 100 newtons minus the coefficient of kinetic friction with the floor. Sorry, I got to go back. I forgot all the numbers. 0.2 kinetic, make sure you get the right one. Mass of system, 10 plus 20 is. And gravity, let's round it to what? All over a system mass of. And so 10 times 30 is 300. 0.2 times 300 is? Or 1/5 of 300? 60. And so this would all be 60. 100 minus 60 would be 40 over 30. What's our acceleration of the system in the horizontal direction? 1.33. Now that's not our final answer, but we just have one more step. Now that we know the acceleration of the system, the blocks individually have that same acceleration. And so now I'm going to go back to block 1's F-net statement. And we said the coefficient of friction with the top 2 blocks was dependent on that acceleration, meters per second squared, divided by gravity. And so notice once again, meters per second squared is going to cancel out. And so coefficient has no unit, move your decimal, it's going to equal what? 0.13. If you want to include the other 3, that's fine. No unit on the final answer. And so actually here, based on these numbers, 0.1 is pretty slick, right? Maybe this would even work with 2 blocks of ice, okay? And so it's not common that static friction is that low, but kinetic would just be lower for it, okay? Questions on a system. By the way, you're gonna see the same-ish stuff coming up in Pulleys because it's a system. Okay, and that's your final answer. And so let's go. I'm still not ready to do the mouse chewing through the licorice. What's on? 17 is, by the way, just some extra practice for you. Maybe we do some, maybe we don't, but it's got, you know, an object at rest. You've got friction between a block and a surface, a skier on a ski slope. Oh, just note to self on that page, this is supposed to be 30 degrees again. And then we've got that, looks like a fuzzy dice. It's kind of like the lady on the helicopter. Okay, so page 18 is going to be our first pulley, minus the mouse and licorice. And I'm going to do some notes on the other side, okay? And I want both pictures visible because we can also call these pulley systems Atwood machines. AP likes to call them Atwood machines, okay? So not that you have to get nitty gritty, why Atwood, okay? I'm guessing it's named after Mr. Atwood, I don't know, or I haven't ever researched it. It's just an Atwood machine. And so notice in the top, you've got this rope. And by the way, no animals were harmed in the making of this physics problem. And you've got ropes. Let's not tie it around the goose's neck, okay? Let's tie it around their waist. Let's keep them secure. Let's keep them safe, right? And so we've got a goose and a gazelle, and it's on either side. And so this is called an Atwood machine when you put one object on each side of that pulley. Now, what's a pulley? Well, a pulley is basically a pivot point for a system, okay? And so this pivot point, and by the way, you'll see pulleys again when in the spring when we do rotation. Right now, this disc that's going to serve as your pivot point, it's not going to rotate. And so here, let's just note to self, in the fall semester, the disc does not rotate. But FYI, in the spring, the disc will rotate. And so right now, if it's not rotating, it's just a pivot point. And so whatever string we have those objects attached to, imagine we've got a slick, maybe fishing line string. It's just going to slip over, okay? And add to the fall, frictionless. In the spring, it'll be with friction. And we're talking about the disc, okay? It's a surface between the string and the disc, right? But for right now, we're going to ignore any rotation. So the mass and diameter of the disc is not going to play a role. And we're going to ignore any friction. That string is just going to slip over the pivot point. Good? Okay. So if we just look at it as a pivot point, all it's doing, it's similar to what you learned previously with simple machines. It's going to change the direction of motion. And so I'm actually going to use this problem to help teach it. Step one, always and forever, is what? Force diagram. We've got two objects. We've got a duck and a gazelle. No, I'm sorry, a goose and a gazelle. Hey, y'all, just so we don't have G and G, our labels, if you want to write out goose and gazelle each, I'm going to change it to a duck. Same spirit, right? Object one, object two, if you don't want to hurt any animals. Okay. And so I'm going to call it a duck and a gazelle. So I can label it with a D and a G for gazelle. Okay. So force diagram, two objects, two force diagrams. And so I'm going to draw it on the side of each animal. And so notice the masses that are given, 8 and 42. So relatively speaking, the gravitational force on the duck or object 1 is going to be rather small, right? So FG duck, or if you want to call it FG1, label them object A, object B, lots of options there, okay? And the gravitational force on the big gazelle is almost 7 times bigger. Now don't grab a ruler, but within reason, right? FG gazelle. Now each of them has a string tied around their waist, right? Their waist, not their necks. Okay. The tension in each string pulls parallel to the string. What direction is the tension force on the duck? What direction is the string pulling on the duck, object 1? Up. It pulls parallel, so the string can't push it down, but it's going to lift it up. Now, trust me right now, I'll explain, but trust me right now, it's bigger than the weight of the duck. Okay? But not as big as the weight of the gazelle. So I'm going to call this the tension force. And at the end of the day, y'all know that if these two forces on the duck were equal in magnitude, would the duck be able to accelerate? And it doesn't say the A word in the problem, but we'll have an accelerating system most times. Okay, what about the tension on the gazelle? It's going to pull what direction? It's also pulling up, right? Strings, they have a tension force that pulls parallel to the string. If the string is above the gazelle, it's going to pull up on it. Now, trust me, it's going to be equal to the magnitude that we just drew for the tension on the duck. Why are these equal? Well, at the end of the day, don't we have a system of two objects? Aren't they going to accelerate together? And you just saw the prior example, when you take a system approach, that I pull on you, you pull on me, the string pulls on the gazelle, it's also pulling on the duck. One is a forward direction, one's a backward direction. Those two are going to be a Newton's third law pair. It's going to be internal to the system, and so it'll cancel out. Good deal? I'll show you how. Now that's it. There's no other forces acting on either object. Are either of them touching the disc that is serving as our pulley? No one's touching. It's gravity and a string. Boom, done. And so the next thing, by the way, I haven't even read the problem. A crazy person attaches a duck and a gazelle to an Atwood machine. Check. Draw the free body diagrams. No components and all forces originate. Check, check. Write your FNet statements in the horizontal and vertical. Do we have any horizontal? No. And so we can say none. What about FNet Y? Well, there's forces on each object in the vertical, so we're going to have 2. And so I'm going to do that down here where I have more room. And so FNet Y for the duck. And then separately, we'll have I'll just do it right below, for the gazelle. And so look at the duck. I have 2 forces acting on it. Oh, one thing we have not done, did they tell us what direction all this is moving? Did they define the positive direction? They have not. So let's think about this. If we release these 2 objects from rest, who's going to win? Who's going to move downward and define our positive direction? Uh-oh. Who wins? The light object or the heavy object? The heavy object. Doesn't it make sense? And plus, notice the weight, the magnitude of our arrows, right? The gravitational force of the gazelle is going to be a positive down, right? Which means that tension on the gazelle would be, even though it's pulling up on the gazelle, it's not in the direction of motion, so it would be negative. And it may be hard to tell where I'm writing, but I'm assigning direction based on kind of who is going to define the direction of the system. Now here is where pulleys change the direction of motion. And you can think about Newton's third law in here too. If the tension on the gazelle is whatever number it is and negative, what is the tension on the duck? Whatever number it is, but positive. Isn't it a true statement that as the gazelle goes down, the duck goes up? And so the duck going up is going to be a positive tension, equal and opposite to the other tension. And so as the duck goes upward, gravity's pulling what direction on the duck? Downward. And so we've got this change in direction. Moral of the story, up is not always positive. Look at that. Up on either one is a different sign. But ooh, I've been preaching. Forward is positive. Aren't they? Don't they have the same forward direction? Watch my hands. If we started both objects, same height, when you release them, gazelle goes down as the duck goes up, right? Think of it as an animated picture, right? So as the gazelle goes down, duck goes up. Forward is positive. They just have a different forward direction. And you got to do that because when we go to write our FNet statements, that's the only way tension will cancel. If you look at it, take a system approach. And so let's write that FNet statement for the duck. We've got a positive tension and minus FGD, the gravitational force on the duck. What about the gazelle? FNet for the gazelle, it has a positive FGD, or if you did A and B, 1 and 2, and then it has a minus tension. And tension, by the way, we got to solve for it. It doesn't say it, but we'll need the acceleration. Those are very, very common with pulleys to either solve for the acceleration and or solve for the tension, okay? But watch. I don't know the tension. All they gave me was masses. That's it. All they gave me was masses. What if I put them together? I'm literally going to add these two equations together because they're both solved for FNet. And so I would have, this is going to be our system, by the way. And so I have FNet of the duck plus FNet of the gazelle equals, what do you notice with Newton's third law pairs? I don't know the number, but whatever it is going to positive number minus the same number is going to cancel out. Internal pairs cancel. Your Newton third law, internal pairs should cancel when you take a system approach. Okay. And so the only thing that remains it's a difference in the weights. FG gazelle minus FG duck. Everybody good there? Notice I didn't draw a system force diagram. It gets a little harder when they're not even touching each other, right? But in the spirit, it still cancels out. And so now what? Well, you could view all this as a system FNet Or you could say MA plus MA, right? Or you could say M duck AY plus M gazelle AY. Well, they're going to accelerate together, similar to our two books. And so you could view it as duck plus gazelle mass. And then you've got a system acceleration. So however you break it down, if you're like system net force, system mass times acceleration, that's usually what I do. Or if you want to break it down, MA plus MA, and then you would just, they have the same acceleration, so it's their combined mass. Get you to the same place. What about on the right side? FG equals mg, so careful here, it's mass of gazelle, and then a slightly bigger gravity, g, right? Minus mass of duck times the same gravity. So even though they're moving different directions, gravity still acts the same direction on each, right? You can factor out the g, and so you can say gazelle mass minus duck mass all times g. Now, I don't know if you've noticed, I really haven't read a question. It said find the tension. Can you solve for the tension if you canceled it out? No. But moral of the story, y'all, if you were to go back up and try to solve for tension, F net equals MA, you need the acceleration. And so you would have two unknowns. You have to cancel one out. And so most times I cancel tension out. Don't worry, we can go back and find it after we find acceleration. So this is very typical. And then last variable step, to solve for the system acceleration, you take the difference in their masses times gravity divided by the sum of their masses. Okay. And not that it's at every time, but a lot of times when it's a side-by-side Atwood machine, this is the format you take, okay? It's the difference in the masses times gravity divided by the sum of the masses. Okay, let's plug it in. They said the gazelle was 42 kilograms, and then the duck, I think, was 7. Is that right? Or 6? 8, gosh. 8. Divided by the sum, and it doesn't matter which one you write first. And so 42 minus 8 is 34 times 10. And then the sum of 8 and 42 is 50. So someone get a calculator. Let me know 6.8 meters per second squared. Now I'm going to box it and know it's not the answer they want, but y'all, half of these problems with pulleys are going to have you solve for acceleration. So we're just not done, but that's the acceleration. Now here's a tip. You ready? Some students solve for acceleration and maybe they get 16.8. They get 16.8. And if I see that, I automatically know you've done something wrong because you got more than 9.8. If an object has an acceleration of 9.8, what's the story? It's in free fall. Can you ever be in free fall if there's a string connecting two objects like this on a pulley? Are they ever going to be in free fall? Not unless you cut the string. They have not done that yet, but watch out, part F, maybe they do. And so you should always, when you have a system with the string intact, you should get an acceleration less than 9.8, okay? It's just a little check for yourself. So now that we know acceleration, it should go quicker. What they actually asked us to solve for what's the tension in the cord after they're released from rest? In other words, they're going to accelerate from rest. Now we know the acceleration. How do I find the tension? Well, I have two equations that involve tension. Now, one's not really easier or harder. Which one do y'all want to use? Because theoretically, you should be able to use them both and get the same answer, right? So do y'all want the duck or the gazelle? Someone call dibs. Duck, okay. And so to solve for the duck, so let's, for part D, let's solve for the FT on the duck. And if there's any rebels in the room, you solve for tension with gazelle. We should get the same answer. And so I'm going to use the duck's FNet statement. And so I'm going to isolate tension. It does not cancel. And so I would get FNet Y for the duck plus FGD equals the tension on the duck. Everybody is in terms of the duck. Muscle memory, FNet equals MA, so it's the mass of the duck times that vertical acceleration, good thing we found it, plus FG equals what, muscle memory? MG, the mass of the duck times gravity. And so mass of the duck was 8, acceleration, a forward 6.8, plus the mass of the duck again is 8, gravity will use 10. And so somebody plug and chug it out. Notice we should get a number bigger than the weight. Remember earlier in the diagram, I said that the tension should be bigger than the weight. I said, trust me, right? If it accelerates upward, the upward force has to be bigger. Oh, so close. 56-ish plus 80-ish. Pledge allegiance to the flag of the United States of America, republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. All right, so if you're listening, I got the numbers, 134 newtons. If you did FNet with the gazelle to solve for tension, you should get the same thing. And then the last thing is asking about how far they move, or how fast will they move? Kinematics. You already know acceleration, good old kinematics. End of story. See y'all next time.